Alright, what is up my homies? Welcome to BrainMelt University. Today we're going to be talking about some basic things about network diagrams and wiring schematic. Although this is primarily a computer networking channel, these are two things that you're going to be working with a lot, pretty much anywhere that you are working in the IT field. Primarily we are going to be focusing on the networking component of this, and we're going to be spending a lot more time worrying about the network diagrams than we are the wiring schematics. But with that said, let's jump right in. What is a wiring schematic and what is a diagram? Well, simply said, a wiring schematic is a detailed view of the wiring in your building or in your campus. This is your way to tell where exactly all of your network cabling is and where all of your electrical lines run. These are both important to understand because your electrical wiring can create electromagnetic interference, or EMI. EMI is that necessary evil that we have to work around anywhere in a network engineer's job. And having your wiring schematic will allow you to lay out your data cables in a direction that it's not going to directly compete with electrical cabling. While some cabling is immune to electromagnetic interference, namely fiber optic cables, it's still not a good idea to run your fiber optic cables in the same places as your electrical cables, just for the sake of separation so that you can keep your stuff separate from the electrician. So with that said, why wouldn't we just use wiring schematics? Why are network diagrams even a thing? Well, the key to wiring schematics is they really only focus on the wiring. They focus on the physical infrastructure in your building or in your campus or your city or whatever scale you're working with. You're not focusing on any endpoints, you're not focusing on any connections, you're really just saying this wire has this endpoint and this endpoint, and it runs this physical location to reach those points. A wiring schematic is not going to focus on whether a router is plugged into a specific port or a switch, or whether there's nothing plugged in at all. Your wiring schematic is there to help you trace wires. It is very important if you're trying to troubleshoot a physical problem where you've already ruled out the rest of the OSI model and you have to troubleshoot why you are not physically connecting one device to another. And usually it's a broken cable, whether a mouse has gotten into a place where it shouldn't and it started chewing on the wires, or whether someone has cut an underground line by digging where they shouldn't, or something like that. So now let's transition to the other side of that. Let's talk about network diagrams. What is a network diagram? Well, a network diagram is a representation of the topology of your network. Now, we should know by now that a network's topology is how everything connects together. Whether we're talking about a physical topology where we are focusing on how each hardware component connects to each other, or whether we're talking about a logical topology, how all of the software is interacting on our network, really determines how we build our network diagram. Your network diagram can focus on either of these two, whether we're only focusing on the endpoints in a logical topology where we're looking at this is a server and these are all of the devices that are pulling information from that server, or vice versa, versus a physical topology where we might be saying this is a router, it is connected to all of these switches which are connected to all of these PCs and all these printers. That is an example of a physical topology. The vast majority of network diagrams that a network engineer would be working with should be physical topologies, but it is important to understand the distinction and be able to recognize those basic differences in our diagram so that we know whether a diagram is going to be helpful to us or whether it's something that we should just move on to a different one. Your logical topology diagrams are going to be more helpful if you're trying to troubleshoot the upper layers of the OSI model, layers 5, 6, and 7. Your physical diagrams are going to be much more helpful if you're trying to troubleshoot layers 2, 3, and 4 of the OSI model. So we kind of see this break in how we do our troubleshooting and which document is going to be the most useful. Your wiring schematic is most useful for layer 1 troubleshooting. Your physical topology is going to be much more useful for troubleshooting layer 2, 3, and 4, and to some lesser extent layer 1, and your logical topology is going to be helpful for helping you troubleshoot layers 5, 6, and 7. So knowing what a network diagram does is great, but how do you actually read one? So we're actually going to jump right in. Okay, so here we are in Visio. Visio is a diagram and table building piece of software built by Microsoft. It is part of the Microsoft Office suite, but it is not included in your standard Microsoft Office subscription. You have to actually pay extra for it. I'm really only using this as a means of demonstrating a number of your most common network diagram icons. There are literally hundreds of network diagram icons, but these are the ones you are most likely to run into on a regular basis. There are a lot of free alternatives to Visio. For example, Lucidchart is a free online service. You can also even use tools like Miro and Xmind, but theirs I haven't really played with that much. Lucidchart does have limitations on the number of objects that you can place in your diagram unless you pay for a paid subscription. But for the majority of students who are just starting out and trying to diagram out their basic lab setup that they have at school, or trying to diagram out their home network, Lucidchart is usually pretty okay at doing that. So let's just go through all of these icons one by one, and then I'll explain what all of these different lines and colors mean. So the first thing that we're going to go through is we're going to go through some legacy devices. These are things that you don't see that often anymore, but you could run into them on your day-to-day job, especially in more rural areas or areas that aren't metropolitan in nature, small towns and cities where a lot of the businesses aren't large enough to have a dedicated IT staff. A lot of their networks are really cobbled together over decades, and so you might run into a large number of these legacy items that you need to actually add to a diagram. So the first thing that we're going to look at is a hub, which is over here. So you'll typically see a hub as either a square or a flat rectangle with a single double-ended arrow pointing left and right. So in this particular setup, this is our hub icon. Now, a hub is a layer 1 device. You should not be using a hub under any circumstances anymore, but you do still run into them from time to time. Now, this particular icon did not come from Cisco. Most of these other icons are Cisco icons, so you'll see these represented in a lot of textbooks just because they're common and relatively accepted as the de facto icon. But there are small variations that you'll run into. So for instance, this particular icon that did not come from Cisco has all of these little dots along the side. Cisco typically doesn't use them because those are used to represent this device. This device is a modem. So your modem, your modulator demodulator, that's what modem stands for, is a device that's designed to take one form of signal and convert it to another form of signal, whether it's trying to convert analog signal into digital signal, like a dial-up modem for dial-up internet, or whether we're trying to convert fiber optic signals into copper signals, or whether we're trying to convert DSL signals into Ethernet signals. That is the job of a modem. It's converting one form of modulation into another. Now, when we're working with more serial type connections, you'll usually run into something called a data service unit, channel service unit, or DSU CSU, or you'll sometimes see CSU DSU. They're describing the same thing. It is a device that is designed to help control the timing on your serial connection, and you really don't see these all that often anymore. Your CSU DSUs are actually either built into the serial cabling itself, or they are built into the actual serial ports on your devices. Serial is an older technology. The bandwidth is absolute garbage by modern standards, but you still see these represented in textbooks all the time. So do keep in mind what a CSU DSU is. It's a legacy technology, and we can usually leave it at that, but you are going to see some certification exams that still ask you what is a CSU DSU and where would you use one, stuff like that. So keep that in mind. Moving over here, we have a bridge. So your bridge is another piece of legacy technology that was designed to be used along with hubs. So a major limitation of a hub was that if one device connected to that hub sent a signal, instead of the hub actually keeping track of where devices were and forwarding that particular message to only the device that needs it, it just shotguns the message out to all other devices connected to the hub. So hubs were also called repeaters, but the problem is if you have a 48 port hub and all 48 ports are connected to computers, if one device sent a message, the other 47 received a message whether they needed it or not. So there was a lot of waste on this network, there was a lot of inefficiencies on this network, and there was a lot of chance for a collision to occur. Now, we're getting beyond the scope of this video, so I'm not going to describe what a collision is, but you will run into that term if you haven't already. So in order to combat this, if we're working with a large network that's say 15 hubs, we really don't want that many hubs all shotgunning information to all of the other hubs, who will then shotgun it to everything that's connected to it. So the bridge was designed to actually keep track of the MAC addresses on our network, and if it received a particular frame, it would actually look to see if it knew where that MAC address belonged. And if it did not belong on the other side of the bridge, it would simply refuse to forward it. So it broke up what was called a collision domain, the area of your network where a collision can occur. So your bridge was basically the only brains that these legacy 1980s and early 90s networks had. But over time, your hubs got more efficient at what they did, your bridges got more and more compact, until someone said, hey, why don't we just take the brain of a bridge, stuff it in a hub, and create a new device that completely eliminates the need for a bridge or a hub? And what they ended up with was a layer 2 switch. So that's what you see down here, is a basic layer 2 switch. You'll usually see these represented as either a square or a flattened cube with two sets of arrows pointing in two separate directions. Now, if I'm doodling this on a whiteboard, I usually just get lazy and I just do one arrow pointing both directions, but that is a network layer 2 switch. Now, your layer 2 switch, if you aren't quite sure what the distinction between a switch and a router is, your switch is normally there to grant some sort of end device connection to a network or to help distribute a network out, but it doesn't allow communication with other networks. That is why we need a router. Now, a router is a forwarding device whose entire purpose is to move information from one network and into another network. So your router, you typically see represented as a short cylinder or a circle with 4 arrows that point in different directions. You'll usually see 2 pointing in or 2 pointing out, but sometimes it's just pointing in 4 different directions. Normally, if I'm writing on a whiteboard, I usually just draw a circle with an X in the middle, and everyone can kind of just make out that that's supposed to be 4 arrows. But you will see a few different variations, but do keep in mind this is a router and it has a very different function from a switch, even though both are forwarding devices. Now, over time, routers and layer 2 switches both have become more efficient at their jobs, and a lot of people, in the same way that we took a hub, put a bridge's brain into it and called it a layer 2 switch, we've actually been able to take some of the functionality of a router, put it in a switch, and create what's called a layer 3 or multi-layer switch. So your layer 3 switch is a switch that still has all of the port density of a standard layer 2 switch and all of the capabilities of a standard layer 2 switch, but some of the ability of a router to separate out networks and to forward traffic between them. In today's day and age, there are still layer 2 switches that are being manufactured, but the number of them has actually grown quite limited. A true layer switch is starting to become kind of a rarity among enterprise networking, and the vast majority are now layer 3 switches to some extent, whether they just have basic static routing capability or whether they have all of the functionality that a router would bring to the table. They really depend on price and manufacturer. But nowadays, even your most basic switches, you have a pretty good chance of having some layer 3 capability. So probably in the next decade or so, you're going to see this move up here to this column along with legacy devices. But for now, we tend to see both in networks. So do keep in mind the difference between a layer 3 switch icon and a layer 2, because that's going to make a big difference in what type of network you're actually looking at. Now, sometimes you might see an icon that looks like a bunch of switches that are stacked on top of each other. They may or may not have the layer 3 icon on the front. They may just have the layer 2 icon on top. This is a switch stack. Now, some manufacturers actually manufacture switches that are capable of linking up with other switches and logically becoming a single switch. So instead of you having to memorize how to log into 4 different devices, all 4 of those devices just share all their resources and logically just look like a single switch. This is what's called a stackable switch, or if you have a bunch of them linked together, it's called a switch stack. So that's what I'm looking at here in this network icon. It is a number of switches that are logically appearing as a single switch, and in this case, This is a layer 3 logical switch stack. Now you'll also see this icon that looks like a brick wall. Sometimes this brick wall has flames coming off of it, and just based on that little piece of information, hopefully you can guess that we're talking about a firewall. So your firewall is a network security appliance. There are tons of security appliances that all have their own icons, but firewalls you tend to see the most. And so I chose to throw this here on this particular list of network icons. Your firewall is a very important piece of your network. If you're working with any kind of enterprise network and they do not have a firewall, you should probably talk to them about adding one. Now, what a firewall does and how it does it, that's beyond the scope of this video, but do keep in mind, if you ever see an icon that looks like a brick wall, whether it has flames coming out of it or not, we are discussing a firewall appliance. Now over here, if you see a cube with an old-fashioned telephone and a bunch of arrows coming off of it, this is what's called a PBX, or a private branch exchange. This is extremely important if you are working with voice over IP or IP telephony. These are both terms to describe using telephones that, instead of connecting to your old-fashioned RJ11 telephone jack, are actually connecting to an RJ45 Ethernet jack and are actually communicating using the internet protocol instead of your basic telephone analog system. So your private branch exchange is a device in your network that allows you to separate all of those calls out. If a telephone call comes in, it looks at the phone number and then it crafts the IP information that sends it to the proper phone within that IP network. This is a very important object if you are working with a company that uses voice over IP. Otherwise, you're not going to see this icon all that often. And lastly, we have the cloud. Your cloud icon is simultaneously extremely important and it's also extremely not important. Your cloud icon is usually used to refer to something that you either don't know how everything else is connected on the other side of that cloud, or it's just such a huge network that you really don't want to have to build a network diagram of that network. So clouds are usually used to represent everything from the internet all the way down to just a network segment where you don't actually have the information to know how everything is connected or what all is in that network. So do keep in mind that your cloud is basically, on a network diagram, a time-saving measure to prevent you from having to do a crap load of research or to diagram out a massive network. So looking at everything that I've described, these are all wired devices or wired representations within your network. There is an entire branch of networking which is all wireless. So you might often see icons like these down here. This object, you can tell because it's just kind of the same icon as a router, but with a couple antennas coming off it. You can probably infer that this is a wireless router, and that's exactly what it is. Your wireless router is, simply put, a router that has wireless capabilities. Every home router pretty much in America is a wireless router, and it typically performs the functions of pretty much everything. It can act as a modem, it can act as a router, it can act as a switch, and it can act as a wireless access point for your devices. Now, this does all of the jobs, and typically the more jobs you try and make a single device do, the less efficient it gets at its jobs. So I usually recommend that people instead get a single router, a single modem, and a single wireless access point. So your wireless access point looks very similar to a switch in most diagrams, with the exception that it has this double helix on the front. This is usually used to represent the electromagnetic waves that serve as the carriers for your connections. Now, your wireless access point serves two jobs. It serves to provide wireless interface to a wired infrastructure, and it has to translate those wireless signals into an Ethernet signal. So your typical wireless access point has an Ethernet cable coming in, and then it just allows other devices like cell phones, tablets, laptops, whatever, to connect back using wireless signals. But at the end of the day, all of those devices that we think of as just wireless all have to go back to a wired infrastructure eventually. But sometimes you'll run into an issue where a company wants a wired network, but they don't want to run a cable to connect certain buildings together. Maybe you might have a company that has a warehouse across the parking lot and they need some basic network in there, but they don't want to have to dig up their parking lot to run an underground cable. They can use what's called a wireless bridge. So your wireless bridge icon looks very similar to your standard bridge, but it does have that double helix in the front. So whereas your wireless access point provides end devices a wireless interface to a wired infrastructure, your wireless bridge provides a wired interface to a wireless infrastructure. So you would normally use two wireless bridges together, which would create this imaginary connection or imaginary bridge to another wired infrastructure somewhere else. So you could shoot a wireless signal across your parking lot to said warehouse in my example, and then an Ethernet cable is going to come back out of that wireless bridge in the warehouse and start linking back to things like switches and the end devices that would connect all of them. Those are your most major wireless type of icons that you will see on a network diagram. Now moving here in the bottom row, you will see a number of end devices. So everything else that I've discussed is some sort of forwarding device. It's something that doesn't use the data for itself. It's trying to move that data to whoever is supposed to receive it. Whereas these devices are an endpoint. They really are not designed for forwarding traffic. They're really just there to utilize it or to provide it to something else. You'll see a lot of these basic icons. So for instance, if you see something that looks kind of like a door with vents in it, that is usually a server. So this server is actually not a Cisco icon. You can tell it's a slightly different shade of blue, kind of like the hub over here, but Cisco often does represent servers in a very similar fashion. So here is one example of a Cisco server. They have dozens of them, but you can tell pretty easily by looking at them that these are both servers. Now here we have a cell phone. Here we have a printer. Now your printer can look like this, or it can actually look like a printer with like a piece of paper coming out the top. There's a number of different icons that can represent printers. You do have a basic computer, which looks like it came from the 1980s, but that's normally just how they represent a desktop. Your laptop generally looks like one that was built in the early 90s, but we can all look at that and say, yep, that's a laptop. And then over here, we have an IP phone. So again, if you're using something that like a private branch exchange, PBX, you're probably also going to see IP phones represented in that same topology. So that's it for icons, but how about how we connect them together? What do all of these different colors and styles of lines represent? So typically an Ethernet cable, a straight through Ethernet cable, is represented by a single black line. Now, they don't normally have these red dots at the end in a network diagram, but I kind of got lazy building this thing. I wanted this to go fast, so I just chose the first solid black line that I could find. But normally, you just have a straight black line that connects two devices. This is a straight through Ethernet cable. Now, it doesn't matter what category or style. If it is a straight through Ethernet, we consider that a solid black cable on a network diagram. But sometimes you'll see a broken black cable on a network diagram. So this is more for legacy networks, and this is to represent a crossover cable. So if you're not quite sure about the distinction between a straight through and a crossover yet, don't worry, you'll be getting to it pretty quickly if you're already to this point. And it's usually used to connect two legacy devices that operate at similar layers of the OSI model, whether they all operate on layer 1, layer 2, or layer 3, then you're going to have to connect them together with a crossover cable instead of your standard straight through. Modern devices have a protocol called auto MDIX that completely negates our need for a crossover cable, but you do still see some extremely cheap devices that for whatever reason do not support auto MDIX. I haven't run into one in quite a while, but I still hear about people who buy them and then get extremely PO'd about it. Moving over here, you'll sometimes see a solid orange cable. So this is used to represent fiber optic connections. Now, this can be a little confusing for people who know that fiber optic cables are color-coded, so we're once again getting off on a tangent, but multi-mode fiber cables are normally orange or sometimes teal, and single-mode fiber is usually yellow. In a network diagram, it doesn't matter whether we're diagramming multi-mode fiber or single-mode fiber, we always use an orange line to represent your fiber cable, so do keep that in mind. Down here, you'll see a red cable that kind of looks like a lightning bolt. Now, red lightning bolts are usually used to describe a serial connection. So a serial connection is, once again, that older style of cabling that requires a CSU-DSU to function. and it is usually used to connect router to router. Once again, it's extremely low throughput by today's standards, so we usually try and avoid using it if we can, but you still see them all the time in textbooks. So do keep in mind, if you see this red lightning bolt cable in a network diagram in a textbook, we are referring to a serial cable. I'll go over this one in a minute, but down here, you'll sometimes see a curled blue cable. Now again, it doesn't usually just have a one-way arrow. I couldn't find a curled line in Visio that didn't have an arrow on it, so I just chose to use this. So this light blue cable that has a curl to it is a console cable. So most of your enterprise devices don't come out of the box ready to go. They're not plug and play like your typical home device. You have to be able to configure them, and because they don't come pre-configured, they don't have an IP address for you to connect to. They don't have a lot of that basic stuff already built in, so you can just plug and play. So we need some way of interfacing directly with that device's operating system, and we usually accomplish that through the use of a console cable. It's usually a light blue cable, although they come in black and white and pretty much any other color under the rainbow. But in a network diagram, we almost always represent them as a light blue cable, and it always has a curl where pretty much everything else is a straight line or angle. Now finally, we come to an ether channel. Now sometimes you might run into a situation where your switch is not able to process enough information to support all of the customer's demands on it. And by customer, I mean everyone at your company who uses it. The fix seems simple, and it would just be, we'll just make another connection between that switch and the one next to it so that it can process twice as much traffic. But in reality, we have a protocol that prevents that from happening, and once again, beyond the scope of this video, we have to do a little bit of back alley trickery to trick these two switches into thinking that these two cables are a single cable. And the answer to that is something called port aggregation or ether channel. So if you're looking at a network diagram and you see multiple connections from switch to switch, and they have this circle that connects them all, this tells you that these multiple connections are operating as an ether channel. And so this basically just means that even though there are physically this many cables connecting these two switches together, logically they are appearing as a single cable that has twice the bandwidth that the two by themselves had. And there you have it. That is the most common objects that you are going to see on a network diagram. If you have any questions, comments, or concerns, please drop them in the comments below, and I will see you all here next time on BrainMelt University.